Unit 12A will be our introduction to sound. Sound is a wave that propagates through a medium, and in a sound wave, what's actually oscillating is the pressure of that medium. So for example, when you pluck a string on a guitar, the string will vibrate back and forth. This vibration will cause for the air particles around the string to become compressed or rarefied, meaning that there are regions where the air pressure is high pressure, that's a compression, and regions where the air pressure is a low pressure, the air particles are spread out. That's called a rarefaction. And when you hear things, this is your perception of sound. Just like whenever you see things, it's your perception of visible light. As that sound wave propagates through the air and travels outward from the source, its amplitude will go down over time because the wave experiences damping, just like we saw in the damped oscillator case. So here's a GIF to help you see how a sound wave actually propagates through air. If you imagine this is like the cone of a speaker on the left here, this piston that's pushing left and right, you'll notice that there are compression waves that travel throughout the air. There are regions of high pressure, which act as a crest in the pressure graph, and there are regions of low pressure, which act as a trough in the pressure graph. So again, what's oscillating in a sound wave is actually the air pressure or the pressure of the medium. It's also important to note that when a sound wave travels, none of these particles actually ever change their original location. They do not move when the sound wave passes by them. Of course, they vibrate in place, but waves do not actually transmit matter. They only transmit energy, and that's true for sound waves as well. So when you're learning about sounds, the volume or loudness of a sound is actually related to the amplitude of the sound wave. And remember, that amplitude will usually be given as a pressure. The pitch of a sound is actually based on its frequency. So the higher the pitch sound, the higher the frequency, versus the lower pitch sound, which would have a lower frequency. And of course, we can change around the amplitude and the frequency to change the type of sound that we get. Actually, the tone or the timbre of a sound is a combination of different variations in frequencies and amplitudes of various sound waves traveling at the same time. So our sound wave, of course, is a wave, and it travels outward from a source, perhaps like a speaker cone, or more appropriately, possibly this tuning fork. If the wave travels outward from the source, it has a wave speed. And we determine the wave speed the same way that we did for our string under tension wave. It is the wavelength times the frequency. And the speed of sound will change depending on which medium you're in. Remember, the wave speed only strictly depends on the medium through which it is traveling. For a sound wave traveling through air, which is the most common sound wave that we're going to deal with, the sound wave will travel at a different speed depending on the temperature of the air. And you can use this equation down here at the bottom to calculate what the wave speed will be for a given temperature. In this equation, capital T is the temperature in Kelvin. So you could plug in room temperature, 25 degrees C or 298 Kelvin, and you would get the speed of sound traveling through air at room temperature. So sound waves travel out from a source, and they travel with a wave speed. This introduces an interesting phenomenon called the Doppler Effect, where an observer will perceive a change in that frequency if the observer or if the source are moving. So in the case where the source is not moving and the observers are not moving, here we have a car that's just got playing a horn, so the sound waves are traveling outward in a spherical direction, and both of these observers, X and Y, hear the sound waves at the same frequency. They are hit by a wave in the same amount of time for every cycle. However, if this car was moving while it was honking its horn, if it was driving to the right, the sound waves to the right of the car will actually be squished together. They will experience a cycle in a greater frequency. And behind the car, in the direction that it's not moving, the sound waves will stretch out. They will occur at a lower frequency than what the original source was producing them at. So the observer on the right side here, observer Y, would hear a higher frequency sound, whereas observer X on the left side would hear a lower frequency sound. even though neither of them are moving, just because the car is moving, it will change the perceived frequency of an observer. So here's an example of a GIF where we have a car driving to the left in this top portion of the diagram. So you can see that as it travels to the left, the sound waves on the left side are being squished together. They are occurring at a higher frequency. They have a shorter wavelength, but they still have the same wave speed. They still travel according to the medium through which they are traveling. On the right side, as the car drives away from this observer, we see that the waves stretch out. They occur at a lower frequency. This person will receive less waves in the same amount of time as the one on the left, and the wavelength is greater. So this person would perceive a lower frequency due to the Doppler shift because this source is moving. We can compare that with the bottom panel where we have a stationary source and stationary observers, and you'll see that the wavelength and the frequency is the same on both sides. Both observers perceive the same wavelength and frequency of sound waves. This effect, the Doppler effect, can also occur if the source is stationary and the observers are moving. They will receive those sound waves at a different frequency. This person who's running away would need more time for each wave to meet them as they are traveling away from the source, and therefore they would hear a lower frequency sound. On the other hand, this person on the right who's traveling toward the car will receive waves at a greater frequency. So they will perceive a higher frequency, even though the source isn't moving and the wave speed isn't any different. Just because the observers are moving, they'll perceive a different frequency of the sound wave. And to calculate this perceived frequency, we can use this equation here that we have to calculate the observed frequency that experiences a Doppler shift. And this equation can be a little bit to unpack, so take it slow. F observed is the frequency that is perceived by an observer. They could be moving or the source could be moving, but they will experience a Doppler shift, and the new frequency that they hear would be F observed. Fs is the frequency of the source. That is the sound frequency of your horn or whatever source is generating that frequency. VW is, of course, the wave speed. That'll be 346 for sound waves traveling through air at room temperature, but it could change depending on the temperature or the medium. V observer is the speed of the observer, and this could either be positive or negative. It depends on how the observer is moving relative to the source. So we would add this speed to this wave speed if the observer is moving toward the source. That'll shift our frequency to a higher frequency. If the observer is moving away from the source, you use a negative here, and that will shift our perceived frequency or observed frequency down. Vs is the speed of the source. So if your car or the source of the sound is moving, you would want to plug in a number here. And that number will be negative if the source is moving toward the observer and positive if the source is moving away from the observer. So we're going to gain a lot of practice with this equation. It's a very important equation for both sound and light. So definitely take your time with this Doppler shift equation. Because sound waves propagate at a fixed speed, something like 346 meters per second in air at room temperature, it is possible for a source that's emitting that sound to be traveling faster than the speed of sound. In this case, we would create something called a sonic boom or a bow wake, which is where the sound waves that are emitted over time can't actually keep up with the object that is emitting those sounds. And this creates a superposition of sound waves, many sound waves adding together as they catch up to the source, such that there is this cone, this shape that forms from the sound waves, which leads to all of them adding up when you actually get hit by this cone of sound. This is called breaking the sound barrier. And when a jet, which is emitting sound at a certain frequency, travels faster than the speed of sound, it can create a sonic boom, which will travel forward and will have a very large amplitude. A wavefront diagram is a representation of the crests and troughs in a wave as it propagates. So here you can see an example of a wavefront diagram. Our source is this tuning fork, and these sound waves travel outward in every direction. There is a peak as this solid line and a trough in the pressure as this dashed line. So these are compressions and rarefactions successively shown in the wavefront diagram. And the way that you draw these is you draw your source as a point, and you draw the waves traveling outward from that source with the crests as solid lines and the troughs as dashed lines. Sometimes we won't show the dashed lines, which are troughs, because it's assumed that between every crest there's a trough halfway through. Sometimes it'll also be useful to show the wavelength, frequency, and wave speed for this diagram underneath the wavefront diagram. As you can see here, I've labeled one wavelength lambda on this wavefront diagram. So here's some other examples of wavefront diagrams. For a string vibrating, it will create compressions and rarefactions in the air around it. For a speaker that has either a subwoofer or a tweeter on top, those will emit sound waves at different frequencies, and we can show that using a wavefront diagram. Or for this bat, which uses echolocation to find its prey, this shows just the crests in this wavefront diagram. So we'll gain more practice with these wavefront diagrams. They're just a visual representation of where the crests and troughs are coming from a sound source. That'll cover everything for Unit 11A. I'll see you in the next one.